Today's speaker, Gina Yuan, is a PhD student in computer science at Stanford University, under the supervision of David Mazieres and Matei Zaharia. Before that, she completed her bachelor's and master's of engineering in computer science at MIT. Her current research interests include privacy, security, and improving the arduous experiences of end users. We're pleased to welcome Gina to present Offload Annotations, bringing heterogeneous computing to existing libraries and workloads at the PL Research Seminar.
Yeah, thanks, Carla, for the introduction. I'm really excited to meet you all today at Protocol Labs. As mentioned, I'm Gina, and I'll be talking about offload annotations for heterogeneous computing on existing libraries and workloads. And I hope you'll all leave this presentation today with a sense of how arduous it is to program for specialized hardware, such as GPUs, and how offload annotations can make this process a little bit easier. And I'll just mention that this is work from a 2020 Usenix ATC paper, along with some of my colleagues and one of my co-advisors, Matei, at Stanford. So there's been a recent explosion in big data, and due to all this available data and the need to make sense of it, data science has become a very popular field. Traditionally, data science has been done almost entirely in Python, a scripting language that's pretty easy to write. And this accommodates data scientists who come from all sorts of programming backgrounds. And additionally, data science started out on the CPU. Together, this resulted in an ecosystem of popular Python data science libraries for the CPU. And even if you don't do data science, you're probably familiar with many of these, like NumPy, Pandas, and scikit-learn. Another trend is that specialized hardware is becoming cheaper and easier to use. What used to be thousands of dollars to buy for yourself can just be rented for a few dollars on the cloud. And as a result, people like data scientists who've never used this technology before are looking for new ways to speed up their applications using hardware. For some background on how GPUs can be used to speed up applications, let's compare them to CPUs. A typical CPU, like in your laptop, might have 4 cores for parallelizing more complex tasks, while in comparison, a GPU has effectively thousands of cores that concurrently execute thousands of simpler tasks. So matrix addition is a good example of an application that would be well fitted to a GPU, which uses each core to process just a single cell in the matrix. However, GPUs also have much less memory than their CPU counterparts, and they can easily crash if they run out of memory. In addition, if you want to use both the CPU and the GPU in the same workload, like if only part of the task can be parallelized, then you have to transfer the data between the two processors to ensure they're on the same device as the function that's using the data. And the time to move data around is proportional to the size of the data and can be a really expensive bottleneck if this data is really big. Now, at first glance, GPUs might seem like a natural fit for speeding up data science applications that process a large amount of data in parallel. After all, there's a lot of cores, and you can process a lot of parallel tasks at the same time. Now that GPUs have gotten cheaper, data scientists are looking for ways to integrate them into their existing workloads. And the result is a similar ecosystem of Python libraries, but for the GPU. These Python libraries are very similar to their CPU library counterparts that we saw earlier. In fact, they claim to mirror the same APIs as their CPU library counterparts. For example, you can see cuDF provides a pandas-like API. CuPy says they can be used as a drop-in replacement for NumPy. PyTorch is a replacement for NumPy, and so on. The idea is, based on this documentation, is that if a data scientist knows how to use NumPy on the CPU, they can just as easily use PyTorch or another library on the GPU. So these GPU libraries all seem to promise a very seamless integration experience, but is it really as easy to use as they say? And I argue that this is not the case, and we'll see in the next example. So here's a simple machine learning workload that started out on the CPU using the CPU library scikit-learn. In this example, we pre-process some input data, xtrain and ytrain, then we train a model, and then we test the model on a different data set, xtest. And at the end, we plot the results. Recall from the previous slide that in most cases, QML's Python API matches the API from scikit-learn. So we try to use this GPU library as a drop-in replacement for scikit-learn. The first thing we do is find functions that can actually be used as drop-in replacements. In this case, we replace PCA and kneighbors classifier. We find that some of these functions don't exist in the GPU libraries, like standard scalar. So we leave the original CPU version in our code. Since we're using both processors, we have to make sure data is on the same device as the function that's using it. Since the inputs to the program, xtrain and ytrain, are usually read from another step in the processing pipeline, we assume they initially start out on the CPU. And we transfer them to the GPU to use on our model. In the testing phase, since the first model is on the CPU, but the second model is not, we transfer the outputs of the first model to the GPU. And then finally, since our plotting library requires the data to be on the CPU, we transfer the results back at the end of the program. Now we run the program and it crashes in the prediction phase because the GPU has run out of memory, which we recall as smaller than CPU memory. Since prediction can be done independently on different batches of data, we manually split the data into batches that fit into GPU memory and then independently predict for each batch. Thus, by paging the data, only a small amount is in the GPU at any time. And finally, the program runs to completion, but it hasn't really gotten any faster. And we also made the code significantly more complex. We think maybe using a different combination of CPU and GPU functions might make it faster. But since we manually inserted all of these statements throughout the code, trying different schedules would also require a lot of manual work. So it turns out that maybe GPU libraries aren't as easy to use as they claim. Our solution to this problem is offload annotations. With offload annotations, or OAs, we have an annotator that annotates CPU library functions with their corresponding GPU implementations, building a bridge between the two libraries. Then instead of manually porting existing code, the end user will simply import this annotated library. Finally, the runtime automatically schedules and pages computation, doing all the things that the end user initially had to do by themselves. I'll discuss the specifics of each role in the following sections. And before we dive deeper into design, our goals are derived from our motivating example. So with less developer effort, we'd like to match the performance of if we wrote the GPU code manually. We'd like to automatically scale to sizes that would normally cause the GPU to crash. And we'd like to beat the performance of using the original CPU libraries. So first, instead of making intrusive changes to the original workload or to the CPU library, the annotator takes advantage of the mirroring APIs and builds a bridge between the CPU and GPU libraries with offload annotations. So in this case, the annotator first has to find corresponding libraries. So NumPy is the CPU library and PyTorch is the GPU library. After identifying libraries, the annotator then identifies the corresponding functions using this OA notation to annotate it. And even though the two libraries claim to have similar APIs, their function names can still differ, like in this example, torch.mul and mp.multiply. The annotator also needs to include the types of the inputs and outputs in each function annotation. And to do this, they use a special type called an offload split type. An offload split type is just a wrapper around an actual type, which in this case is NumPy's ND array. The offload split type allows our runtime to dynamically ensure that chained functions are compatible in type. So here we have the inputs and the outputs, which are just variants on ND array type. The annotator can also annotate allocation functions, which are just functions that don't have any inputs. And this will help us later minimize costly data transfers in our scheduling algorithm. So now that we have the function annotations in place, let's dive deeper into what is in an offload split type. For each offload split type, the annotator has to implement an interface that conveys additional information to the runtime for scheduling. The first two function calls of this interface make up the offloading API, which is on the slide here. The offloading API is used to automatically transfer data, which is what we had to do manually in the motivating example. So first, the device function specifies whether the value is on the CPU or the GPU. In our implementation for the ND array type, we use Python type checking to see if it's a torch tensor or a NumPy ND array. The to function transfers data from one of these devices to the other, so like from the CPU to the GPU. And our implementation uses the transfer API from the PyTorch library to move data around. The next three function calls in the interface of an offload split type are part of the splitting API. The splitting API returns the number of elements in a value, and it also describes how to correctly split data into data parallel chunks and then merge them back together. And since NumPy's ND array is a matrix, the splitting API that we implemented is essentially matrix operations over the value. This is the same as in previous work on split annotations from SOSP. The split annotations runtime is called Mozart. And while Mozart uses the splitting API for cache pipelining on the CPU, we're leveraging the splitting API to automatically page large data sets on the GPU. Note that the splitting API is optional for the annotator, and it's not always possible if the data cannot be split into parallel chunks. Overall, the interface for the offload split type can be easily generalized to many types. We were able to implement it for other types like pandas data frames or machine learning models in scikit-learn. So now that the annotator has created an annotated library bridging the two CPU and GPU libraries, the end user is the person who's actually responsible for writing application code. In this case, the application is just a Python program that uses many of the functions that we previously annotated, like multiply and square root. The end user doesn't have to be the same person as the annotator. And in fact, we imagine an open source ecosystem similar to TypeScript, in which a small number of annotators write annotation files that can be shared amongst a large number of end users. To use the annotated library, the end user simply imports the annotated library instead of the CPU library. And now the program, instead of calling the actual functions, they call our annotated wrappers to these functions. These wrappers lazily evaluate the value. So if we actually need to use the value or materialize it, such as to use in a plotting library, we explicitly call an evaluate function. This function invokes the runtime, and as we'll see in the next section, the end user doesn't need to be aware of any of the data transfer, scheduling, or paging that they had to do in the manual example. So now we're on to the runtime that automatically manages a lot of the execution. So each time the program calls an annotated function, the runtime adds to a lazy computation graph of the execution on the left side. The graph on this slide corresponds to the same Python program from earlier. The nodes in the graph represent function calls, and the dotted lines represent an allocation function. The edges represent data dependencies between these function calls. When evaluate is called, the runtime does a topological sort of the graph and produces a list of instructions on the right. Next, our runtime block will assign functions to either the CPU or the GPU based on a simple algorithm. Basically, if the function has an annotation with a GPU library, Bach will assign the function to the GPU, and otherwise it will assign it to the CPU. For example, argsin didn't have a GPU implementation, so we put it on the CPU, but the other two functions do. Other workloads can implement a more complicated scheduling algorithm based on their specific needs, and we'll discuss how to do that later. Next, the runtime assigns allocation functions to a device. So the algorithm for this is to look at the first function that uses this data and then assign the allocation to the same device. So for example, since node 2 was assigned to the CPU, node 1 will be allocated to the CPU as well. And then node 3 is on the GPU because of node 4. This minimizes data transfers, which, as we remember, is expensive, because if node 3 had been allocated on the CPU initially, then we would have to transfer it first. So now that all nodes in the graph have been assigned a device, Bach uses the offloading API that the annotator implemented to automatically manage data transfers. For example, the outputs of node 2 need to be transferred to the GPU to be used in node 4. And at the end, it needs to be transferred back to be used in a plotting library. How the runtime does this is it uses the device function to check the location of the current input, and then it uses the to function to transfer the input if necessary. If the splitting API is implemented, then we estimate the size of the working data set using the size API and compare it to the size of GPU memory. If it doesn't fit in the GPU, then the runtime uses split to split the data into a manageable chunk, and then executes the entire series of instructions before splitting the next chunk. That splits the data. And then at the end, we use the merge API to merge the values back together. And altogether, by leveraging the offload and splitting APIs implemented by the annotator, the runtime can automatically manage data transfers and scheduling in an environment that uses both CPUs and GPUs. So to improve on the naive scheduling algorithm that defaults to the GPU, we introduce a way for the scheduler to make slightly more informed decisions based on some heuristics implemented by the annotator. So consider this example where the runtime is trying to assign node 4 to either the CPU or the GPU. It'll do a cost-benefit analysis of executing the function directly on the CPU, which doesn't require any data transfers, versus transferring the inputs to the GPU, which may take a long time, and then executing the function on the GPU, which could be fast because it's in parallel. At large data sizes, like 2 to the 28, it might be totally worth it to transfer the data, since computing on the GPU is so much faster. Now, if the data size is smaller, it might be faster to just do the compute on the CPU and avoid the overheads of computing on the GPU. So in this case, based on the heuristics, the scheduler would assign the runtime, or the scheduler would assign node 4 to the CPU. In the code, the heuristics are actually Python functions that the annotator provides. These are functions of runtime data, like the offload split types of the inputs and the inputs themselves. The estimators in this graph are functions of the input data size. So as the data size, so the CPU cost has like a linear estimated cost, while the GPU cost has an overhead for the data transfer. For the compute. So below a certain data size, the heuristic favors the CPU, and above it favors the GPU, just like we saw previously with the scales. Additionally, the heuristics demonstrate that the runtime captures a variety of information that can be automatically leveraged to make more informed scheduling decisions. This can be important as the workloads become increasingly complex and we have more and more heterogeneous hardware in our environment. So next, we'll discuss how offload annotations performed in practice. So we wrote offload annotations for 4 different GPU libraries, and we found that the library integrations took on average 130 lines of code. We paired some of the libraries that claim to be drop-in replacements for the CPU libraries from earlier, like CuPy for NumPy, cuDF for Pandas, QML for scikit-learn. The actual implementation looks very similar to what we described previously in the talk. We evaluated the runtime Bach on 8 different workloads from library tutorials, Jupyter notebooks, and blog posts that we found online. Across all the workloads, we observed a maximum speedup of 1200x and a median speedup of 6.3x compared to their original CPU implementations. And this is all with much less developer effort. So our experimental setup looks something like this. We evaluated each of these data science workloads on 3 different implementations. The CPU library indicates the original workload before we made any modifications to port it to the GPU. The GPU library indicates a handwritten GPU implementation that uses the library as a drop-in replacement as much as it can, much like our manual example. And then Bach indicates offload annotations by importing an annotated library into the code. On the x-axis, we vary the input data size on a logarithmic scale. And on the y-axis, we measure the end-to-end runtime, which is also on a logarithmic scale. And then we use log scale because otherwise the data is very cramped. So that's just something to keep in mind. The dotted line on the graph indicates where the GPU implementation runs out of memory. So in this graph, in the GPU library, the runtime is proportional to this data size until it runs out of memory and then crashes. We'll look at the, Okay, so the first takeaway is that without manually replacing functions in your code and writing data transfer statements, Bach can match the performance of handwritten GPU implementations. There's a little bit of overhead due to the overhead of our scheduler, but due to the logarithmic scale, this actually isn't very much. So from this, we can conclude that at the same data sizes, the two implementations have very similar runtimes. Now, second, without manually splitting and paging the data in the code, Bach can automatically scale to data sizes beyond where the GPU library runs out of memory. In the graph, Bach extends the dotted line, extends beyond the dotted line with no additional effort. And then finally, Bach consistently beats the performance of existing CPU library implementations, leveraging the new hardware that has become available to data scientists due to the commoditization of the cloud. And note that due to the log scale, the difference in runtime actually represents a constant multiplicative speedup. So in this case, it's 6.8x. And then as it gets, as it has to page data sets, it becomes 2.3x. We evaluated 8 workloads in total, and this is a summary of our results. So as you see, the speed up's up to 1200x with a median of 6.3x. And next, we'll discuss some of these graphs individually to see how some of the features that we implemented in the scheduler affect the runtime. So first, we'll see how allocations affect the runtime. So recall from earlier, we schedule allocations by putting them on the same device that first uses the, as the function that first uses the data. So when the data size is smaller, we can allocate directly on the GPU, which allows the performance of the Bach implementation to match closely with the GPU library implementation. However, when the data no longer fits in GPU memory, we're unable to allocate directly to the GPU because it doesn't fit. So instead, we have to allocate first to the CPU and then page it into memory. That's why beyond the dotted line where the GPU runs out of memory, we're unable to get the same performance benefits that we did from when the initial working set fit in memory. So crime index still saves time, which is crime index is the workload, saves time by eliminating the initial data transfer, but this only works while the allocation still fits in GPU memory. Next, we'll evaluate the heuristics, which is what we used as a more complex scheduling algorithm. And we use a simple heuristic, which is based on the data size. So in this example, TSVD, at smaller data sizes, the workload schedules all the computation on the CPU because of the overhead of transferring of computing on the GPU. And at larger data sizes, it'll transfer the data to the GPU. So essentially, this heuristic allows us to get the runtime that's the minimum of both the CPU library implementation and the GPU library implementation. And then finally, in this workload, we evaluate the benefits of paging datasets. This is the same workload as our motivating example, where we have a model that we first train, and then we test on some data. So the fitting, the phase where we train or fit the model dominates the runtime initially, while the data size is small. But as the size of the test data increases, we are able to page this data into memory. And in this case, the prediction time will dominate the runtime. So as the data size increases, because Bach is automatically able to page the data set, even when it no longer fits, the absolute runtime advantage also becomes more significant, enabling speedups of up to 6.2x. So in conclusion, porting existing libraries and workloads to use heterogeneous hardware like the CPU and the GPU can be quite arduous, despite the promises made by the targeted GPU libraries. With less developer effort, Offload Annotations makes it possible to match the performance of handwritten GPU code. It allows your workloads to automatically scale to data sizes larger than GPU memory. And it allows you to beat CPU performance for a data scientist with a less programming experience with the GPU. Our code is open source on GitHub if you'd like to try it for yourself, and you can find my contact information on my website.
Oh, fantastic. Thank you, Gina, for a really exciting presentation. And now I'll open the floor up to questions. You can either ask directly, or if you don't feel like being on the video, you can just text the question to me in the chat and I will read it out.
I was curious if you could go into a little more detail on what the open annotation process looks like for like adding new libraries or functions to the annotation system.
Yeah, so what that would look like in practice is similar to like these slides here. So you'd have to have a file that kind of represents a new library. And this library will import the old library and the GPU library and then build a bridge between the two. And so like one option could be like uploading this to the Python package manager and then downloading this annotated library. Or I haven't really built the actual, like, even though we imagine this being done in an open source framework, maybe there could be like some like specific, some package manager specific to these annotated libraries. But yeah, I think if we were to like take this project to the next step and actually like be inviting people to write their annotations for this system, we'd have to like build the framework for people to like submit to some like central repository.
Yeah, that makes sense. I'm wondering if there's something like, I imagine there could also be some kind of automated analysis and annotation system that would either through like type signatures and test data identify what the parallel version of the CPU function is and try and match things in a more like automated, less human intensive way.
Oh yeah, that would be great to automatically generate these annotations instead of like having someone manually go through. Although I guess if you could manually generate the annotations, then you could also generate the replacement for the code. But I guess the point is that it's kind of hard to find the parallel functions without some like human intuition.
Yeah, I think that even if you only do like, even if you only annotate a fraction of them, it's still useful. Whereas if you only have if you have a fractionally effective substitution system, then that becomes far less efficient.
Yeah, that's true. It also might be useful as like GPU libraries or CPU libraries evolve, and then you have to get different versions compatible with each other. It'd be great to have an automated step to aid the process.
But this work allows you to have incremental transfer over of like as soon as some automated library can identify these are the functions that we can realistically swap between CPU and GPU, then like you don't need complete translatability or complete annotation.
Mm-hmm. Yeah, since this is in Python too, which isn't really like, it's kind of a typed language sometimes, that could affect like how you can automatically generate these.
Yeah.
Other questions? If you have a pressing question that you don't want on the video, we can get to that after the video. I have one that I think comes from what you just mentioned. How much housekeeping is involved with keeping this up to date, with making sure that you're compatible with existing libraries? When there's a change to libraries, do you have to do a lot of updating, or?
I guess this can probably be discussed in the context of like generally keeping packages up to date for your software project. So I think developers put in a lot of effort to keep versions of their libraries backwards compatible for a while at least. So ideally that would work similarly in this case. I guess if there were like breaking changes, then you would probably have, like if your original project was going to migrate to a new version of a library that has breaking changes, then similarly there would need to be a new version for the annotations. Yeah, I guess it's interesting because you have to consider two different versions of software, whereas you'd only consider one previously. But hopefully if we have like some sort of automated process, that would make being able to test these compatibility changes much faster. But yeah, I think like dependency management is definitely an annoying part of software engineering, and it'd be great to improve that process.
Any other questions for the presenter?
I'd be curious how you would expect efficiency to scale if you had one system that was hooked up to multiple GPUs. I would assume that like the heuristics would still work, and that like the computation graph would still, like it feels like most of this would work well in theory, but I'm curious about what your perspective is, if you think it would work well in practice.
Yeah, I think in theory, it makes sense that if you can parallelize your computation, having more like GPUs, you could parallelize across all the GPUs. I think something that we found in our workloads, especially the more data science workloads compared to the machine learning ones, is that the computing on the GPU takes such a short amount of time that most of the runtime is dominated by the transfer time. So if you also have a bunch of GPUs, you need to first transfer your data to each of these GPUs. So whatever hardware you have for transferring the data might be the bottleneck in this case, rather than the compute. But maybe if it's more compute intensive, then fitting this into that kind of workload would work well. And there's also this library that I haven't really looked into, but I'm vaguely, so Dask, I believe, is aware for like automatically managing distributed computation. And there's also a Dask GP, like QDF version. So since these automatically distribute computation, I'm wondering if maybe you can just annotate these libraries. So then our system, the offload annotations aren't actually aware of the distributing, but the libraries that you're annotating it with are. But yeah, I think data transfer is a huge bottleneck in these heterogeneous applications, that it doesn't seem like it is until you implement it. Yeah.
Follow-up question, actually. So since, well, the Crossfire isn't a thing anymore, right? But I'm actually curious whether you have some idea of whether inter-GPU links would actually be. I mean, would it still obviously transferring from CPU to GPU over the PCI Express bus does carry some significant penalties? Would inter-GPU links be fast enough that they would die with the cost? I mean, obviously, it's still better if you can operate pairwise in a way that operates the GPUs separately, right? But I don't have a good sense for what the impact would be if you actually needed to synchronize between GPUs.
I guess as a practical workload, I can think of where you need to synchronize between GPUs. It's like when you're training data sets and there needs to be some like coordination between them. I'm not too sure how this would fit in this workload in this framework, since it's for like frameworks with like very clearly defined data parallel chunks. Perhaps it could be expressed somehow with like the splitting and the merging functions, and like, you know how there's a to API, maybe instead of just transferring between a generic CPU and a generic GPU, maybe there could be some concept of different devices that exist within your heterogeneous framework. So like transferring between GPUs. Yeah, it'd be interesting to like get a sense of these kinds of workloads and see if you can like observe a pattern based on these workloads that you can generalize into a software interface. I don't know if that answers your question.
Yeah, I mean, I'm not sure there is an answer. I'm also not too clear on the current status of mGPU implementations, right? Since SLI and Crossfire were deprecated, but you know, even things that just require memory transfers across GPUs because they exceed the size of the RAM, right? So yeah, I don't know. It was just curiosity.
Hi everyone. I hope you enjoyed this research seminar. If you have suggestions for a future speaker, or if you'd like to present on your own research, please email us at research@protocol.ai. I'm also really excited to announce that we've expanded our grant offerings to include PhD and postdoc fellowships, Young Investigator Awards, research sabbatical funding, and a number of other funding opportunities. You can check these out at grants.protocol.ai. To make sure you don't miss other announcements like this, sign up for our mailing list and specify what types of emails you'd like to receive. The link to do this is in the description below. Don't forget to like and subscribe and share this video. Thanks for joining, everyone. We will see you next time.